Welcome to this explainer. I'm going to be your systems architect today, and we're jumping right into one of the absolute most critical structural components in modern deep learning. We are looking at the fundamental wiring diagram of neural networks, the Jacobian. Now, if a standard derivative tells you how one single scalar output changes when you nudge one scalar input, well, the Jacobian scales that entire concept up. It is the complete instruction manual for sensitivity across whole vectors. And trust me, truly understanding it is the difference between writing elegant, efficient code and literally instantly crashing your hardware.
Okay, let's run through our diagnostic checklist for this session. We've got the wiring diagram, the engineering bottleneck, the VGP workaround, the volume knob, and finally, systems in production.
Section 1. The wiring diagram. Let's map out these local sensitivities.
To really understand the system, we have to look at the math beneath it. A neural network layer essentially maps vectors to vectors. So if you're mapping an n-dimensional space into an m-dimensional space, you don't just have one simple derivative anymore. You have n outputs, and every single one of them is dependent on n inputs. The m by n Jacobian organizes all of those partial derivatives into a really rigorous structure. It's essentially the instruction manual that lists the sensitivity of every single gauge to every single dial in your machine. Row I tells you exactly how gauge I reacts to all the dials, and column J tells you how all the gauges react to dial J.
But you see that Jacobian isn't just some abstract array of numbers. It represents a physical deformation. Picture a standard 2D grid of dots. As a function is applied to it, that entire grid stretches and twists. If you focus on one specific square of that grid and watch it get pulled and distorted into a parallelogram, the Jacobian is the linear approximation of that precise physical distortion. The columns of our matrix are quite literally the vectors forming the newly stretched edges of that parallelogram. It is a highly precise physical mapping of space.
Moving to Section 2, the engineering bottleneck. This is where scaling up hits a wall. Let's look at the dimensions of a standard linear layer in a modern large language model. It typically maps a 4096-dimensional vector to another 4096-dimensional vector. If we want to know the sensitivity of every single output to every single input, we're looking at creating an explicit Jacobian matrix of exactly 4096 by 4096 dimensions.
Now, attempting to compute every partial derivative explicitly requires m separate forward passes. Storing just this one matrix in standard float 32 takes up about 67 megabytes per layer. If you actually tried computing this across, say, a 100-layer model, especially with batched data, you'd watch your memory bar instantly fill up with red, hit 100%, and just crash. It is a visceral, catastrophic, out-of-memory hardware crash. It's an entirely unviable system architecture.
So how do we fix it? Section 3, the VGP workaround.
This is where the absolute miracle of reverse mode automatic differentiation, what we call backpropagation, comes in. We don't actually need that massive explicit Jacobian. Because we're ultimately mapping millions of parameters to just one scalar loss value, we really only care about how that specific scalar loss changes. We can use the Vector-Jacobian Product, or VJP, to get the gradient for all inputs simultaneously in just one O of 1 backward pass. It costs roughly the same as a single forward pass, has minimal memory overhead, and we completely avoid ever materializing that massive matrix.
Think of it exactly like a billiards shot. An upstream vector V comes in from the right, that's representing the desired change in the output space. It strikes the Jacobian wiring diagram, almost like hitting the rail of the pool table, and bounds off to the left as a completely new vector. That new vector is your gradient in the input space. It turns this impossibly complex web of partial derivatives into a beautifully simple, highly efficient pathfinding operation. You just project your desired output backward through the system to find the exact required input change.
Let's test this with a quick numerical diagnostic. Imagine a simple 2D function. We compute our partial derivatives and construct the matrix. Say we evaluate it at a specific input, like x equals 1, 2. First, we might find a determinant of -27. What that means is our local patch of space is scaled in area by 27 times, and that negative sign? That means its orientation is flipped, kind of like turning a glove inside out. Then, running our VJP pathfinding operation with an upstream vector of 1, 0, we get an output gradient of 2, 1. This instantly diagnoses that to increase our target output, input x1 is exactly twice as important as input x2.
Which brings us to Section 4, the volume knob.
If your system models probabilities, like a generative model does, you absolutely must account for how space stretches or shrinks.
probability mass has to be conserved. If the mathematical transformation stretches space, expanding the volume, well, the probability density must decrease to compensate. The Jacobian determinant is the exact scaling factor that tracks this volume change. Without it, you would incorrectly assume your data is more or less dense than it actually is.
But here we run into another severe system bottleneck. Computing the log absolute determinant for a general n-by-n Jacobian requires LU decomposition, which is an O of n cubed operation. For a 4096-dimensional matrix, that demands roughly 68 billion floating-point operations per layer. Just like the memory crash we saw earlier, this computation time makes high-dimensional probability modeling effectively impossible to run.
System engineers are clever, though. They solved this by designing architectures like normalizing flows using what are called coupling layers. Basically, they force half of the outputs to just copy the inputs directly, and the other half are simple functions of that first half. Structurally, this guarantees the Jacobian is a lower triangular matrix. And here's the trick. The determinant of a triangular matrix is just the product of its diagonal entries. Instantly, the computational cost drops from O of n cubed down to O of n, bypassing the bottleneck entirely and keeping the system online.
Finally, Section 5. Systems in production. Let's look at how this is actually deployed.
So the crucial point here is that your specific interaction with the Jacobian defines your entire system's efficiency. In backpropagation, we use the VGP to skip the matrix. In normalizing flows, we calculate the determinant for density tracking. In adversarial robustness, the Jacobian defines the first-order approximation used to craft attacks. And in meta-learning, like MAML, you actually have to differentiate the gradient update step itself, which involves the Jacobian of the gradient, better known as the Hessian. The blueprint of this wiring is quite literally everywhere.
Even in wild, cutting-edge systems like neural ordinary differential equations, the Jacobian remains central. Instead of storing all those intermediate states to backpropagate, the adjoint method defines an entirely new ODE to evolve the gradient backward continuously through time. The ODE solver just computes the VJP implicitly on the fly. This brilliant piece of systems engineering drops the memory requirement for tracking gradients over time down to an incredibly lean O of 1.
As we keep pushing the boundaries of deep learning into implicit mathematical modeling and continuous flows, we run into the ultimate question. We've spent years figuring out how to compress, bypass, and implicitly calculate this matrix. Will future AI architectures figure out how to bypass this wiring diagram entirely, computing sensitivities and volume changes without ever explicitly knowing the forward function at all? It's the next great frontier in system architecture, and definitely one worth keeping a close eye on. Thanks for joining me on this system diagnostic. Keep exploring the wiring.